Hi, welcome to the 6502 show. Today, I'm going to take a look at a language from the very dawn of microcomputing, PLM, and specifically a flavor for the Motorola 6800 and the Flex operating system. There's next to nothing on PLM on YouTube, and not a heck of a lot more on the internet in general. So this is going to be my little contribution to take a look at a subset of PLM, SPLM, and what it has to offer. But before we can do that, let's take a look at the language in context, at the time it was written and the machines it was written for, and at some of its background. Why indeed, IBM? Why do you need to develop yet another language? It turned out that IBM's customers back in the early 60s were having trouble when they wanted to expand because IBM was building computers just for accounting or just for engineering. So instead, what they decided to do is take a new tack, and they developed the IBM 360 system. PL1 was the language that was going to run on it. They wanted to take the best of Fortran, of Algol, of COBOL, and kind of smash it all together, and what came out was Programming Language 1, PL1. Lots of videos on YouTube about that, so you can check those out. Okay, let's move ahead about 6 or 7 years to the early 1970s. It is the dawn of the microprocessor age. One of the guys who was an early adopter and enthusiast was Gary Kildall, a computer scientist at the time teaching at the Naval Postgraduate School in Central California, not too far from where Intel was located. They had just come out in 1972 with the 4004 and the 8008 processors. These, especially the latter, these were the things that kicked off the microcomputer revolution. Kildall was really enthusiastic about these chips. Intel lent him a number of machines, such as this Intellect 8. Well, not this exact one, but you know what I mean. He had a great time interfacing it, and for Intel, he came up with PLM, Programming Language for Microcomputers. It was the very first high-level language targeted at an 8-bit microcomputer chip. This is the very first thing. It kicks off everything that follows. CPM, which Kildall's company, Digital Research International, developed, was written in PLM. And as we know, all modern operating systems for personal computers owe a debt to Kildall and CPM. They wouldn't exist without his work. It only took a few years for manufacturers like Motorola to come out with the 6800 8-bit microprocessor, and swiftly on the heels of that, a number of companies started offering computers, such as the Southwest Texas Product 6800, the Smoke Signal Broadcasting Chieftain, the Sphere. Lots of other machines were being made and being bought in the mid-70s. Well, a full floating point BASIC running on these machines was the holy grail, and MITs on their Altair 680B machine were able to do just that. It was up to a young engineer named Tom Crosley, who decided he needed to program in a language that he knew best, and that was PLM. So he decided to write a small version of it. At the second West Coast Computer Faire in San Jose, California, way back in 1978, he described the language and how it worked with a twin cassette system, because back in those days, floppy drives were very expensive. And what he did is he decided on the critical elements of PLM that would run in his 20K system, and soon enough, he had it running. The resulting subset he called SPLM for small PLM. Let's take a look at some of the features of this neat little language. Instead of spending hours paging back and forth through 5x7 dot matrix printed manuals, documents, what I've decided to do is I made a little crib sheet for myself, and I thought I'd share it with you. This goes through everything. I got it on just 2 pieces of paper, And it was invaluable as I started learning this language. The language is block-oriented, structured programming, and here are some of the things in the order in which they are presented in the manual. We have the ability to add a comment. We can identify labels as such. They have to be declared before they're referenced. And the types of constants and variables we have here, they can be designated as numbers in decimal or hex. And let's see what else we have. You can have one or two characters, which will be interpreted as ASCII. And if you want to make long strings, you just define them as data and then call their label later on. You've got two kinds of data that you can enter into a variable. You can have a byte or you can have a 16-bit address. Doesn't have to be an address, of course. You can count all the way up to 65, 535 if you want. You have all the basic operators with some logic as well, and that is a really wonderful thing when you're doing some bit manipulations. Makes life a lot easier. And the big one here, assignment, that's a no-brainer. It's a let statement. But down here at the bottom is a really important note. You have to make declarations of all your variables. They can't be done on the fly or programs will just crash. And this calls for a little bit of forethought. Unlike BASIC, this is not a great language for just hacking stuff together. Program flow control is handled with if then and else and then do loops. There are no go-to statements as in PLM. And it was planned for version 2.0, but I don't think a version 2.0 ever came out. This is version 1.2, which works with the Flex operating system. So you can do some pretty complex things with do end and do while. And you define your procedures as subroutines, blocks of code that are going to do things. And you would call those procedures. Like so. You can call by a specific address. If I just wanted to output whatever was in the accumulator, I could do that. Or I can call a label. And you can get out of them early with the return statement. This is essentially peek and poke, direct memory access, mem-a and mem-a being for 16-bit. And you can also embed code directly, machine code, directly into your program. So we could call routines in the swatbug ROM, or we can declare that this is a message and then would generate the opcodes for loadx with the address of that message, and then just call pdata1 in swatbug. You can embed all kinds of things in there, separate little machine language routines that you want to call and use for quicker access or that just don't make sense. And it's easier, maybe you've got a library, subroutines, you just want to jam it in there. Great, you've got a way to do it. Well, with that out of the way, let's take a look at an actual program. Here we have an old standby, Chuck-a-Luck. It's about as easy as games come. It's been around for hundreds of years, and the computer version of this has been floating around on systems for well over 50 years. Well, as you can see here, this is not particularly well structured. We got a lot of go-to in here. We're doing piles of it. And yeah, this isn't going to be a lot of good in a structured programming environment like SPLM. So what we need to do is figure out what's happening in this program, procedure by procedure, block by block. Let's identify those, and then we'll build them in SPLM one at a time. If we take a close look at Chuck-a-Luck, we can break this down into 8 distinct steps that we need to take to play the game. These are, we need to print the instructions and initialize the player's money. And then we'll start the main loop, and we'll take in a bet, test it. Then we'll choose a number on which to bet, and make sure it's good. Then we're going to throw 3 die. Then we're going to print those values and determine the total number of matches. Finally, if there are no matches, we'll subtract money from a given procedure that does that. Otherwise, we're going to call the winner's procedure and see if they won even money or double or triple. Then we're going to check the player's bank, finally, and see if the player has busted or if the dealer's been cleaned out. Otherwise, we're just going to repeat the main game loop over and over until the player decides that they want to quit. So what do those steps look like in SPLM? Let's take a look. We're going to print the title, and then we're going to give our player $500. And then the main game loop begins. So while the player still has money, we'll print a couple of line feeds, and then we'll call a procedure called make bet. Then we're going to come back from that after the bet is made, and we'll check the status. If they bet 0, then they wanted to leave. We'll just say thanks, and that'll be the end of that. If the bet was good, we'll call make bet, and we'll also fall through to what would be the good bet routine. Then we're going to choose a number. And if the bet status is bad, or is 0, rather, then we'll call choose number again. It was bad, so when we got to go back and do it again and say, no good. But if it was good, then we're going to roll 3 dice. We'll print 3 dice in that procedure, and we'll call the matches procedure to see if we got any matches. And if there are no matches, well, we'll call that. Otherwise, we'll call winner and then determine how much money the player won. Finally, we'll come back from either one of these two, and then we'll check to see if the player's busted or if the dealer's been cleaned out. This is the end of that do while loop up here, and that constitutes the entire program. Again, this is just calling procedures over and over. Let's see what they look like actually when they're broken down into their component parts. This list grew. I believe it stopped originally here, and then it just, as I built the program, and kept making new modules, I found I needed more variables, so I put them in here one at a time. And they can have pretty descriptive names. Input buffer, clearly, bet status, bet amount, true false, number of digits, etc., etc. Also, all of our strings are defined here in terms of data tables. The labels give them an address that I can then call and put that into the X register, call SWAT bugs, print out a line of ASCII, and it'll do it. So basically, I'm making strings right here. Not basically, I am. Grabbed Technical Systems Consultants random number generator routine because, hey, if it ain't broke, don't fix it. And now we just get into the procedures. This, for example, is just an in decimal. I'm going to take in 1 decimal. And I've got, I'm going to use Flex's input a decimal number routine. I'm going to do a little BCC on it. And again, I've put that in directly into the code in line. Then we'll check the carry flag and do what we need to do. Either we need to print the bet amount message, or we're going to see how many digits we've got going on there. Output digits. Here's our roll 3 dice routine, where I'm going to call the random entry routine, which is up there. Actually, this is peak. DA is going to equal whatever byte is in the result of calling random enter. So that's the TSC. That's the TSC random number routine. We'll get a result. We're going to stick that in dice A. Get that result, modulo 6 it so that we're between 0 and 5, and then add the 1 to get between 1 and 6. Works just like every Microsoft Basic, TSC Basic random routine you've ever seen. We do that 3 times. If a procedure calls another procedure, that procedure has to appear lower in the program than the calling procedure. Let's see. For example, call print carriage return line feed. So I've got a little thing up above that does that. But that had to be defined up above, not down here anywhere. It had to be defined lower in memory. And we're checking so there were no matches. This is what we do. Is the player busted? Do we have a winner? And we're going to add, money equals money plus whatever the value of his winnings were if he matched 1, 2, or 3. And that's the end of the program. When we hit an end point, we'll just print out some type of message and call warm start. And that was defined way up at the top. Our very first procedure, warm start, jump to the flex warm start spot. That could be changed to anything you want it to change when you want to end the program. So that's Chuck-a-Luck written in SPML. Well, and of course, it's not a lot of fun to just sit here and go through the code other than for our personal edification and knowledge building. Let's go play the game. Okay, Flex is up and running. I have my disks loaded, and right now you can see I've got a directory up of my SPLM disk, my work disk. I've got the compiler on it. See if I can highlight this. Yeah, there's the compiler right there. And our little program is chuckluck.command. SPLM, the compiler, made just a straight up binary. It's just, machine code. And if you don't put any flex specific things in there and it's just straight 6800 assembly code, it'll run on anything. Do not need the SPLM compiler. There is no runtime environment that has to be loaded. Okay, let's run Chuck-Luck. Here we go. Pick a number from 1 to 6. We'll roll 3 dice. Match 1 pays 1 to 1. Match 2, 2 to 1. All 3, 3 to 1. Win $5,000 to clean me out. Bet 0 to leave the game. You have $500. Make a bet. Well, let's just go crazy here. 200. Let's bet on lucky 3. Hey, I got a match. All right. Well, now I'm feeling cocky, so let's bet on 6. I missed. So I lost the $400 and I'm down to 3. Make a bet. Well, let's just go for it here. Number on which to place bet. 1. Match 1 time. All right. So clearly you can see what's going to happen here. It goes round and round and round in that do while loop, just like we were seeing. Let's hit the 0 to quit the game. I'm going to bet nothing. It just says thanks for playing and returns me to the warm start to the flex prompt. With good old Chuck-a-Luck working, and as exciting as it is, I thought it might be fun to give the language a little more of a workout and see what the compiled code would look like and what it would do by building one of the worst snake games the world has ever seen. All right, here goes nothing. Whee! Uh-oh, went the wrong way. Yeah. Uh-oh, hit the wrong key, ran into the wall. Oof, not good. I think the best I've done on this was about 78, and it's upper 70s, and by that time I was just playing it to see if I could play it. But proof of concept, you can write a Snake game without video memory. Voila! I was fortunate enough to run into Tom Crosley on the internet, and I got to ask him a few questions about SPLM. And he told me that while he didn't really recall that the source code has survived for any version, he did verify that in addition to the Motorola 6800 and Flex versions and the cassette version he made originally in 1978, there were versions for the Apple II and the IBM PC. These are long gone. I can't find them anywhere. If you know anything about SPLM running on an Apple II or an IBM PC, drop me a line. I'd appreciate it. Well, there you have it. SPLM, a very workable and usable subset of the PLM programming language right from the dawn of microcomputer programming. You know, this is a real piece of computing history, and I've placed a flex disk image onto my website that has SPLM on it, and it's ready to go for any Flex 2 or 3 system. Also, Flex 2 and 3 users have another compiler that they can use, BASIC, and it has its own dialect and flavor of BASIC. I've run a few programs through it, seems to work just fine, so that gives you yet another option. Details in the description down there. Well, thanks for watching the 6502 show. As always, it is my pleasure to bring it to you and explore pieces of computer history. So I hope you did like this video. If you do like it, hit the button. You can also subscribe to keep up to date on new videos when they come out. And hey, tell a friend or two about us. How about that? Okay, so enough nonsense. Till we see each other again, you take care.